So welcome you all. In the last lecture, we have studied about different communication interfaces. So today we are going to start a new topic and very interesting topic, that is real-time operating system. So we know that there are operating systems for different personal computers, right? So those cannot be used directly, so because we have to satisfy some real-time constraints, right? So for that, uh, uh, the operating system is used, that can perform in a real time, right? So what is actually the real-time systems, right? So real-time systems basically, you know it is a time is a quantitative notion, right? For example, uh, you consider a plant, right? So if temperature exceeds certain threshold, right? So there should be some action, there should be some alarm, or there should be some action on that, right? If there is a fire in the any industry, so there should be some cooling system which should be started on time, right? So in a real time system, one of the important thing is the deadline is must. Okay, the deadline is must. So all the tasks should meet the deadline, right? However, in the traditional operating system, the the time was a qualitative notion. Okay, so qualitative notion means, so suppose the task has started, right? So we give a qualitative notion that task should be completed before the next task, okay, or it should be completed after this time, right? But the time is not a physical time there, right? But here we talk about the physical time. Physical time is, let's suppose that let's another task can be started after 100 second or 200 second, right? So this time is a quantity, physical quantity, and that is fixed, right? That is not a qualitative time. So that's why we call it as that real time operating systems are time constrained response, right? So what is the meaning of time constraint response? So in a real time operating system, not only it should get the accurate output, the output must be accurate. Not only that, but also it should satisfy the deadline. Okay, if your system is producing an accurate output but it is failing to, or it is not meeting the deadline, right? So let's say that you have to complete a task in 100 millisecond, and if it completes at 105 millisecond, or let's say that it completes at 150 millisecond, right? So that means your or any system, or your system is not meeting the deadline, right? So that means your system has failed, it is considered as failed, right? So all real time, so real time operating system is mostly used in embedded system, but all real time systems are not necessarily embedded system, right? So this real time operating system is inherent in the embedded system designing, right? But it is not necessary, right? So there could be other real time systems as well. For example, you are monitoring an aircraft, right? So aircraft is landing and it is taking off, so all the parameters should be measured, right? So it should also, it is, this system is also working in a real time, but it is not embedded in the aircraft, right? So from the airport you are monitoring all these things, so this is working in real time, but it is not embedded in the products, right? So but many of the systems the real-time operating systems are embedded in the system, right? So this real-time systems are embedded system or safety bound. Safety bound means it is very important that it should meet the safety. It is safety critical. What is the meaning of safety critical? For example, if the response of the system is not within time, right? So it could cause different damages such as property damage or life damage, etc. Right? So that's why the real-time operating system can be used in either in embedded system or it is used in safety critical systems, right? So and one more thing is, as I told that it should meet the deadline. So all the tasks in the in the RTOS should meet the deadline. That is the main constraint of this RTOS, real-time operating system. Okay, so the job of this operating system is not only working in a real time, but it should meet the deadline. And to meet the deadline for each task, RTO has task scheduler, right? So basically, when you talk about a simple embedded system, for example, it's just a temperature controller. So you are having an oven and you have to do some temperature monitoring. So if the temperature exceeds or go below certain threshold, it has to do some action, right? So if it is a simple temperature controller, there may not be need of any real-time operating system. But if your embedded system is quite complex, for example, the nuclear submarine or rocket, right, or any other automated system. So there might be many tasks which embedded system has to handle, right? All these are embedded. So we need some software which can control all these tasks, right? There should be some synchronization. There should be some all the tasks should meet their deadlines. Which tasks are more time critical, right? Or which tasks are more actually emergency tasks, right? So there could be many tasks. So when embedded system cannot control all the tasks, right? So if you want to write all these synchronization or scheduling at a particular time, your code length will become so large, right? So therefore we need a separate software which can not only maintain the synchronization between all the tasks, but also maintain other features such as deadline of each task, which task should be started at what time, right? Everything should be decided by external software, and that is your real-time operating system. Okay, so the real-time operating system has a task scheduler. So we will study what is actually the task scheduler. So we will study that what are the kind of task schedulers. So how the RTOS is different from a general operating system. So if you talk about a general operating system, the objective of general operating system is to minimize the response time of each task and maintain fairness. Fairness means, for example, some task is coming at a certain time, so I will give fairness to each task, right? So for example, some tasks are coming at a coming now, so I will give first priority to that task, right? So I want to ensure the fairness that first come first serve, right? But in the embedded system, it is not necessarily to give fairness, right? But the idea here is to meet the deadline, right? Because the task should meet the deadline. That is the more constraint. So even if you complete a task before the deadline, you will not get any reward in the embedded system, right? So rather, your more focus is to meet the deadline rather than a fairness or to minimize the response time of each task. So in short, we can call it as that RTOS should meet a real-time constraint, that is deadline, and correctness, right? So you should focus that all the output should be correct. Also, it is needed for multitasking. Okay, so that's why we can ask a question that why not, why do we need this operating system? I can do it in the program itself. Whenever I am writing a program for a particular task, so there I can do all these things. So as I told, that RTOS is very very important to maintain all the task synchronization, multitasking. If there are so many tasks, if it is a complex system, then scheduling, timing of each task, memory management, right? So some of the tasks are taking memory, right? So memory is also very limited in this real-time systems, right? So there should be an efficient use of memory for each task. So memory management is done by operating system. Then file system, there are different file systems that could be managed, security issue, right? Networking issue, power management, etc., right? So the idea here is not to just develop a new operating system for the embedded system, right? Because in embedded system, one of the important constraint is time to market. One of the important constraint is time to market. So if you are going to design a complete new operating system for different embedded system, it will not able to meet this time to market metric, right? Because one operating system can take several years to develop, right? But we have to launch our product in the market, right? So we have to satisfy the time to market constraint. So the idea here is reuse of component, reuse of components. So what is the meaning of reuse of the components? So as we talked about IP, intellectual properties, so intellectual properties can not only be in the hardware but also it is in software, right? So we have the general purpose operating system. So the idea here is we don't need the full functional operating system, right? But we can take some of the functionality from the general purpose operating system or any other existing embedded system, operating system, or a real-time operating system. Okay, so no need to develop the full operating system again. Rather than we want to reuse the components, right? So we can buy from other company those IPs, those particular IPs. Okay, so those IPs can be in the hardware component or in the software component, right? And this operating system changes with different varieties of processor, right? So we have to develop different operating system, right? So we are so that's why there is a this is also very handy when we use a particular processor, right? So if you are going to develop a new operating system, that will be very much time consuming. Okay, so rather than in the embedded system, the approach is to reuse the components, right? Because there is no single OS which fits all. So the operating system, there is an object oriented approach, right? So you know that object oriented means object oriented programming means we can reuse those particular objects or their class or their subclass, right? So no need to use the complete program, rather than we use different objects for our particular application, right? So if you categorize the real-time operating system, they can be categorized into three categories. One is hard real-time system, soft real-time system, and firm real-time system. So here we are not talking about, first of all, RT operating system, real-time operating system. So first we'll talk what kind of real-time systems are there, and then we use RTOS for those real-time systems. So what are the real-time system? One is actually hard real-time system. So hard real-time systems are the systems where you have to meet the deadline exactly. Okay, you have to meet the deadline exactly. Okay, for example, you have an industry. Okay, if there is a fire, the coolant system should start immediately. If it is not started within a time limit, you can have damage of life and property, right, and other things, right. So the idea here is, so let's say that this is your time constraint. So within 0 to 20 millisecond your certain task should be initiated, right. So it does not matter if your task is completed at 25 millisecond, even if the task is accurate, but if it not meeting the deadline, this system is called as, the system acts as a fail, right. So the system completely considered as failed system. Okay, so we consider here utilization of that system is 0. Okay, 0% utilization, that means there is no utilization, there is no use of that system. However, in the soft real-time system, as an example you can take as a safety critical industry system. Okay, it could be a numeric basically any nuclear reactor or any other industry factories where fire sensor has to be initiated within a time, right. So in soft real-time system, the deadline is not necessarily met, but the it is giving accurately output. For example, the deadline is, let's say, the D, and it is completing after some time after the D, right, but it is giving some output. Okay, so utility is not considered 0 here. Okay, it is not considered 0 here, rather than we can call it as the performance is degraded. Okay, but utilization is not 0, right. For example, we see that reservation system, or we are using web browsing, right. So for example, if your output is coming after certain time, okay, that will not cause any harm. Okay. So let's say that you're browsing it and your browser output should come within a 20 millisecond, right, but it is coming after a 25 millisecond, there is no harm, right. So these kind of real-time systems are called as soft real-time systems, and we just call it as, if it is not meeting the deadline, we call it as, okay, the system is slow, right, or it is, the performance of the system is degraded. So, right. So the third types of real-time systems are firm real-time system. So firm real-time system means when your system is giving output after the deadline, the system ignores that output. For example, in video conferencing system, or any other picture transmission in a TV. So what is happening, that some frames are arriving late, right. Some frames, image frames are arriving late. So system will simply ignore those particular frames, right. So if there is a flicker also, or any other kind of distortion, so system can ignore that, right. It does not consider into the final output, right. So still in this case also the utilization is not considered as 0, right. So there are different types of tasks. Okay, as I told that we have to complete certain job or certain task, right. So the task can be categorized into different categories, 3 different categories. One is periodic task, another is aperiodic task, and a third one is sporadic task, right. Okay, so what is actually periodic task? Periodic task means it occurs with regular time. For example, a task is coming at let's say that this is your time. Okay, so let's say that task Ti is coming after 4 seconds, then next it is coming at 8 seconds, and it is coming at 12 seconds, right. So in this case, the task, we know that task will come at every 4 second or 4 millisecond. Okay, so here the idea here is that all the the tasks are coming periodically in a periodic manner, and most of the tasks in a real-time system are periodic. So for example, you have designed an embedded system. Okay, so let's say that you have designed a weather monitoring system, right. So what they are doing actually, so they have some temperature sensor or humidity sensor or any other sensor, right. So the sensor has to monitor every 10 seconds or every 1 minute the environmental parameters, right? So actually we know that these sensors will be active after every 1 minute or 2 minutes, whatever the time you want to specify. So these tasks are periodic, right? So in real time most of the tasks are periodic tasks. Second type of task can be categorized as aperiodic tasks. So aperiodic tasks are random, right? It can come anytime, right? And these are soft real time. Soft real time means, for example, I have a certain system and I give a command that okay, you do this, right? So I should have the command. Okay. For example, any IoT system or any other monitoring system, I should have the authority. So if I give a command, the system should do that, right? So for example, I'm using a mobile phone, right? So if I want to I want to do some, I want to click pictures, or I want to search something on the mobile phone, right? So these tasks, these commands can come randomly. Okay, these are not fixed, and these are soft real time. Soft real time means the deadline, even if it is not met, that can be considered. Okay, so utilization is still not zero, right? Yeah, so if I have not defined the utilization, so let me define that also. So utilization means utilization means it is considered as, for one task utilization, if I write one task utilization, that is defined as the execution time and divided by the period, right? So this is your, so we know that these tasks are coming at 4 seconds, the next task will come at 8 seconds, the next task will come at 12 seconds, right? So the execution could be 1 second, it could be 2 seconds or 3 seconds, even it can be more than 4 seconds, right? So this task has to hold for some time, right? Then only, if it is more than 4 seconds, the task should be at hold at some place, right? And then it is called back whenever the processor is free. So, right, so that I will not talk about later when we will study the schedulers, right? But the task utilization is defined as the execution time upon the period, right? And if you define the overall task for all tasks, you have to sum for all the tasks, right? So for all I, right? So yes, so the last types of task is sporadic task. Okay, sporadic task means it also occur randomly, but these are hard real time. For example, in an industry system, sensor has detected some fire in some industry, right? So cooling system has to start within a time frame that is also fixed. So within 10 millisecond, if 10 millisecond or 1 second, let's say, that depending on the criticality of the system, if it has not started in that particular time, it can cause a huge damage. So sporadic tasks are hard real time, and they occur rarely. They are random, but they occur rarely because these are not the emergency events. Okay, so all the real time tasks are generated due to some internal or external events. So internal means, so sensors are generating those tasks, or user can give an external events, right? Then what is actually task scheduling, right? So we have so many tasks. Okay, so for example, in a nuclear reactor, there are so many tasks. So reaction should be started at a particular time, then it should be monitored, right? So if heat is generating at a above threshold, the cooling system has to be started. Or if you talk about in a monitoring system, that every 1 minute moisture sensor, other sensor has to be started, right? Then they have to communication takes some time. So these are actually different tasks in each and every system. So there should be some task scheduler, right? So which will decide that when the task will start, right? And when the task will start, and in an efficient way, so that all tasks should meet their deadlines. Okay, but as I told, that fairness is not guaranteed. So even if I complete certain task early, I will not get any reward, right? So the idea here is to meet all task deadline. So that's why the role of task scheduler. So before going into different types of task schedulers, we will actually study different terminologies. So what are the different terminologies? So first is task arrival or release. Okay. So whenever any task, suppose the sensors are sensing. So this is one task. So the task has arrived. Right. So this is called as released. Task has arrived or task has released. Right. So next is actually job. Job is nothing but a unit of work or a task instance. Okay. So for example, as I told that there are many tasks which has arrived at the same time, right? So I cannot give, let's suppose some task came Ti and it takes some time. Let's say that it takes 100 millisecond time to complete this task, right? And the same time another task is also coming Tj and that takes 50 millisecond, right? So what I will do, rather than I am assigning this Ti task for 100 millisecond, I can divide the task into some instances. Okay, so let's say that instances are 10 millisecond, right? So Ti will execute for 10 millisecond, then another task has come, then that means this task will be executed next, right? And then this will be in hold. Okay, let's call it as T1, let's call it as T2, so that this is a queue. Okay, there is a queue. So when T1 is executing, T2 has arrived, right? So this is T2. So whenever T1 is executing here, T2 has arrived, right? So what will happen? The time is assigned only 10 milliseconds. So this has to go here. So T1 is here. So now T2 will come here. Okay, we will study in more details when you will study the schedulers. So this is brief I am telling. So what is happening? This one job, okay, one job is divided into time instances, or this is called as task instances, right? So this is a unit of work or a task instance. So this is called as job. Okay, so this is full task and this is job. This is which is executing at 10 millisecond, right? And what is the task? Task is nothing but a sequence of similar jobs. Okay, so sequence means it has to run 10 times. If your time is assigned only 10 millisecond, it has to run 10 times. So that is called as sequence of similar job. And there is something called absolute and relative deadline. So what is that? So whenever this task is released and it starts executing after some time and it completes here, and this is absolute deadline before which it has to complete, right? But it completed here. So that this basically from here to here, releasing time to the deadline, actual deadline, is called as relative deadline. Okay, absolute deadline is very easy. So it's a complete quantitative number, physical quantity of clock, right? So it's a certain clock that after 100 millisecond is a deadline. Okay, task should be completed within 100 millisecond. That is the actual or absolute deadline. Then next is response time. What is the response time? So response time is nothing but whenever the task has arrived and it has executed. Okay, it is a little bit different than, it does not matter that it is completing exactly on the deadline or it is completing before. So from here to here, if I write down, so this is your response time. Okay, so next is actually one more terminology, that is so the objective in the soft real-time system is minimizing the response time. However, in hard real-time system, it is to meet the deadline. So then there is some other terminology, that is phase. It is phase in the task scheduling. So as I told that whenever the task will arrive, it will not execute immediately, right? Because there might be some other task which will be executed, right? So it takes some time to execute. Okay, so the time is called as phase. Okay, time is called as phase and it is denoted as phi. Okay, this is a phase. So what will happen actually, after that this will executing periodically. Okay, so for example, here this is, let's say that rocket So you are launching a rocket, right? Initially it will go with its own inertia, right? It will not change, right? Then you can control it. For example, it is going initially for 2 seconds, let's say. So this 2 second is the phase for this task, okay, and after that you can actually change its direction or a speed or any other thing, right? So what you are doing actually, so every 50 millisecond you are changing the direction, right? So that's all. So for first millisecond, so you can call it as period is 50 millisecond, let's say. So every 50 millisecond actually I can control it. So 50 millisecond is your relative deadline, right? And it can execute 10 milliseconds. So from here to here it is 50 millisecond and execute somewhere here, okay? So this is the execution time, right? So this is the terminology in phase terminology in task scheduling. Now something called valid schedule and feasible schedule. So what is that actually? So at most one task can be assigned to one processor, okay? So valid schedule means if the schedule is valid in terms of what? So one valid is that task is completely ready or not, okay? First it checks that all the constraints are ready or not, okay? And then it assigns one task to that processor. It simply does not actually assigns whenever it comes. First it checks that it is valid or not, okay? Valid means it has mentioned all these parameters, such as what should be the relative deadline, what should be the absolute deadline, right? Or what is the previous output. So if it is depending on other task, so that previous task has got output or not, right? Previous task has output or not, right? So it is checking that all the resources are free from previous task, okay? Or suppose this new task is taking the output from the previous task that has come or not, okay? So all these things it checks. That is your valid task, valid schedule, okay? But it does not mention the deadline, okay? It does not mention the deadline, okay? Valid schedule is not mentioning the deadline. But if along with this, if you mention the deadline also, then it is called as feasible schedule. So okay, all these should be all these things should be satisfied along with the deadline. So that is why feasible schedule is nothing but valid schedule with deadlines, okay? Now there are three more terminologies, that is proficient scheduler, equally proficient scheduler, and optimal scheduler. So what is that actually? So proficient scheduler means it is just a comparison of schedulers. So for example, scheduler 1 can execute a certain task, but it is not able to meet the deadline, right? So it is actually not able to meet deadline. And there is a scheduler 2, right? There is scheduler 2, so it is able to schedule with a certain deadline, right? So what is happening? So S2 is able to schedule a feasible task, okay? But S1 is not able to do that. That means it is not able to meet the deadline. So that is why we call it as S2 is more proficient scheduler than S1. So S2 is proficient than S1. And there is something called equally proficient. That means some task is executed by a S1 scheduler, the same task can be executed in the same manner by S2 scheduler also. So that means all schedulers are equally proficient. Optimal scheduler means, so if any scheduler is scheduling task with too much of feasible way, right? So by satisfying all the constraints, it is optimal in all sense. So that is called as optimal scheduler, right? Then there is something called scheduling points. So what is that actually? For example, this is a time stamp, right? So a scheduler decides here at this time instant that which task will be executed at what time, right? So then after some time there might be new tasks which are arriving, right? So then again at this time that scheduler decides that which tasks are to be scheduled and what time. then again this is the point, then this is the point. So these are called as scheduling points. Okay, so this is time. This is called as scheduling points. So these are actually two types. Schedulings are basically two types. One is clock driven and another is event driven. Okay, so clock driven means there is a periodic timer, right? So for example, we have fixed it. So we have fixed it that with a certain clock that after every 5 millisecond I have to schedule a task. Okay, so first I will schedule at 5 millisecond, then I will schedule at 10 millisecond, then 15 millisecond, and so on, right? So this scheduling is prefixed, right? Beforehand only we have fixed it. So whenever the interrupt comes, it has to schedule a task. Okay, so that interrupt is coming periodically with certain clock. However, in the event driven case, there are some events are driven, right? So for example, there might be some hazardous events, or some sensor is sensing some data, right? So it has detected some anomaly, or let's say that whenever the new events are coming. Okay, so for example, you are monitoring something, or let's say that traffic system monitoring. So whenever the new car is coming, or a new vehicle is coming, right? So there is some event which is happening at some time, right? So this time could be random here, but here whenever any event is coming, I have to schedule a task, right? So some task might be coming at 10 seconds, it may take 50 milliseconds for coming to the next task, right? So whenever the new tasks are coming, so suppose one task came here, another task came here, another task came here. So whenever the events are coming or events are generated, then I will schedule a task. So that is called as event driven task, right? So these are the basic terminologies which we will use while studying different types of schedulers, right? And third type is also there that I have not mentioned. Let me write that also. Another is priority driven. So what is actually priority driven scheduling? So some tasks are higher priority. Okay, for example, as you can take again example of any factory where some fire has occurred, right? So it is very high priority event, right? So immediately the cooling system has to start. Okay, so scheduler should immediately assign that task first by holding all the other tasks. This is very high priority task, right? So based on the priority also we can decide the scheduling, right? So the next class we will study different types of scheduling, such as